Welcome to the fourth course in Geostatistics, focused on kriging and co-kriging. The main topic of this course will be interpolation and map generation. I am Marcel and I will be serving as the lead instructor for this course. Today we will be working on the final lesson of this fourth Geostatistics course, which is the lesson 5, focusing on ordinary co-kriging. The key topics we'll be covering in this lesson include the selection of the relevant variables, exploratory data analysis, spatial modeling of this data, model validation, and finally the application of the model through the creation of various types of maps. It is worth noting that in this lesson we'll be utilizing QGIS exclusively for the entire project, even though R is integrated. This is particularly interesting aspect as we have yet to come across any article or content that solely use QGIS to complete a geostatistic project based on Co-kriging interpolation technique. We'll be pushing the boundaries in the world of statistical geography. I would like to note for all the new users in the Geo RGB community that this fourth Geostatistics course has been covering topics related to various interpolation techniques with kriging. For instance, in the first lesson we discussed ordinary kriging, in the second universal kriging, in the third kriging with regression, and in the fourth kriging with external drift. Today, in lesson 5, we'll be focusing on ordinary co-kriging. By the end of this course, with all the lessons combined, it represents over 20 hours of content. If you wish to have access to all this content, you can sign up on Geo RGB community website at gscourse.online. Through the e-learning platform, you will be able to download all the scripts used during the lessons as well as the datasets, so that you can independently repeat the exercise and see the results for yourself. If you are interested in following along, you can also find us on our YouTube channel. The same content from the website is uploaded to YouTube, but any premium lessons will have some restrictions. This means you won't be able to see the codes or scripts we use during the lessons, which is part of the premium content that is only available on the website. However, you can still follow along with the lessons on YouTube. Just be aware that some parts of the content may not be fully accessible. It is worth mentioning that not all the lessons content is restricted. Some parts are completely open and you can see the codes we are using. Now let's start with the lesson. First, I would like to provide a brief summary of what the 5th lesson of the 4th course in Geostatistics will be about, and mention that this lesson is a continuation of the lesson 9th of the 3rd course in Geostatistics that we completed previously. The principles and the foundations of the co-kriging were already explained in that lesson, so many things will be omitted in today's lesson. To have a complete understanding of the co-kriging technique, I recommend reviewing that video tutorial before watching today's lesson, as the linear regression model of regionalization, which is used to successfully apply the co-kriging technique, was already explained in that lesson. Now that we have mentioned this, let's move on to the summary. Today we'll be working with two sets of data. One set of data contains the target or the variable of interest, which will be the variable that will be interpolated. In this case, it will be the chloride concentration at a depth of 30 centimeters. On the other hand, we have the auxiliary variable. In this case, the auxiliary variable will be the soil electrical conductivity, also measured at 30 centimeters depth. The target variable, the chloride concentration, will be obtained through laboratory analysis. Therefore, a series of samples, in this case 120 samples, will be sent to the laboratory to analyze the chloride concentration. The auxiliary variable that we will use to obtain a better prediction of the chlorides will be the soil electrical conductivity measured in the field. But this conductivity will be measured using field instrumentation. This means that the cost of the sampling and obtaining the conductivity results is much more economical and accessible than the chloride concentration obtained from the laboratory. The point of using Co-kriging is to improve the prediction of the target variable with a reduced cost, so it uses an auxiliary variable that is cheaper and easier to obtain and will ultimately produce better results than if we only use the target variable for the interpolation. The first dataset presents 3 different variables, all of which were measured at a depth of 30 centimeters. The main variable is the concentration of chlorides in soil, followed by the soil electrical conductivity measured in the laboratory and the soil electrical conductivity measured in the field with the instrumentation. In this first set of samples, we can see that the samples are randomly distributed. We have areas with high sampling intensity, but other areas with very poor sampling. In the second set of samples, we have a systematic sampling, and the samples were taken, each one 400 meters apart, both for the x-axis and the y-axis. In this case, we only have one variable, which is soil electrical conductivity measured also at the depth of 30 centimeters with the field instrumentation. This set of samples contain 134 samples. This set of samples contain 120 samples. And the link between these two sets of samples is the soil electrical conductivity measured with the field instrumentation, because this parameter is in this set of samples and is also in this set of samples. So through that variable, we can link the two sets of samples. So in total, the variable associated with the soil electrical conductivity measured with the field instrumentation has 254 samples, which is the sum of these samples plus these samples. Then the variable of interest has 120 samples, which is the concentration of chlorides in soil, and it is this set of samples. The variable that we will use to calibrate the whole system will be the soil electrical conductivity measured in the laboratory. That variable will help us to calibrate the model to verify that the soil electrical conductivity measured in the field with the instrumentation is appropriate and does not have any errors. After introducing the variables, our next step is to analyze the data distribution. We will examine the histogram of chloride concentrations and the histogram of electroconductivity measured with the field instrumentation. We will also use a box plot to see the normality of the data, the median and the mean. Later, we will perform a data transformation to improve the results of the Co-kriging. We will transform the data using the square root of both the auxiliary variable and the target variable. Afterwards, we will verify that the electroconductivity measured in the laboratory and the electroconductivity measured in the field are highly correlated, indicating that the field instrumentation and measurements are adequate and correct. In this case, as we can see, the correlation is nearly perfect, indicating that we don't need to make any calibration, as the correlation is practically 1. We also have to verify that the main variable of interest, which is the concentration of chlorides in soils, and the auxiliary variable, which is the electroconductivity measured with the field instrumentation, are highly correlated, and this correlation is linear. This condition is very important and indispensable for successfully executing co-kriging. If there is any nonlinear correlation between these two variables, we don't be able to perform co-kriging. Afterwards, what we will do is analyze if there is any type of trend in the data. The goal is to ensure that the data presents stationarity, so that we can apply the Kriging interpolation technique. If there were any trend, then it will have to be removed first, so that we could work with the residual values. Therefore, it is important to determine the existence or not existence of a trend in the data. In this case, it has been proven that the concentration of chlorides against the x coordinates does not show any type of trend, and the values are randomly distributed. The same thing happens when we use the y coordinate. We can also use the Semivariogram cloud to identify any kind of trend in the data. In this case, we can see that for the chloride concentration, the Semivariogram cloud doesn't show any trend. There is no outlier values and there is no clustering, where, for example, a group of samples is separated from the main cloud of points. In the case of the Semivariogram cloud of the electroconductivity measured in the field, we also don't see any outlier, clusters, or any kind of trend. The experimental Semivariogram is also very interesting for identifying trends. In this case, we can see that the data shows a spatial structure reaching a seal and indicating that there is no trend in the data. This can be seen in the experimental Semivariogram for the chloride concentrations, and the same happens for the electrical conductivity measured with the field instrumentation. In both experimental Semivariograms, we can see that the data shows spatial structure, which is a necessary condition to be able to perform co-kriging. We need that the data variograms, the one related to the chloride concentrations and the one related to the electrical conductivity, present spatial structure. And the cross-semivariogram between these two variables also has to present a spatial structure. Later on, we focus on the area where the experimental Semivariogram presents the spatial structure, which is the beginning of the Semivariogram up to 1,500 meters. And then we use the experimental Semivariogram to fit the model for both chlorides and electrical conductivity. We need to remember that we are only interested in the part of the graph that shows a spatial correlation. This part of the graph is at the beginning. In this case, at the beginning, what we do is plot the experimental Semivariogram over the entire stand. In this case, it's about 6,000 meters. Later, when we see where the structure of the data is, what we do is focus only on the part that presents the correlation. In this case, it is the first 1,500 meters in both cases. Later, what we are going to do is fit a model. In this case, we are going to fit the spherical model in both direct experimental Semivariograms. Things we need to consider here. Well, first, it is important to consider the number of samples pairs we have for each lag. As you can see, in the case of the chlorides, it is much smaller than in the case of the field measurement conductivity. The point is that in this case, we have almost double the number of samples that we have for the chlorides. So in each interval, in the field measurement conductivity, we have more samples pairs. So this indicates that the experimental Semivariogram we can get with the conductivity is much more robust because it has many more samples than the experimental Semivariogram we get with the chlorides, where you can see that the number of samples varies between 100 and 300, but in the conductivity it varies between 200 and 1,300. The fact that the number of samples for chloride concentration is not very large. We have already said that there are only 120 samples force us to work exclusively with the omnidirectional experimental semivariogram, because we know that it will provide us with the most robust semivariogram. However, in this case, we cannot consider working with directional semivariograms because they wouldn't be very robust, because the number of samples we could get will be very small. So the semivariogram wouldn't be representative of the data. For that reason, in this exercise, we are only going to work with the omnidirectional experimental semivariogram. When adjusting the model, it is important to be aware that applying Co-kriging has many restrictions. Co-kriging offers many advantages, but to be able to apply it, the conditions are very restrictive. In this case, we need the model to be the same for both the experimental semivariogram of the target variable and the experimental semivariogram of the auxiliary variable. We need to have the same model, in addition to having the same range. The only parameters that can differ is the Nager effect and the partial seal. Later, we will create the cross-experimental semivariogram with the concentration of chlorides and with the electrical conductivity. The result will be this experimental semivariogram, which we can see here, which is the result of joining this experimental semivariogram with this experimental semivariogram. And this is the new one that we created, which is the cross. Here we have the representation of the three experimental semivariograms. This is for the electrical conductivity, this is the cross, and this is for the concentration of chlorides. Subsequently, and after making a series of modifications, we reach the model for Co-kriging, where we can adjust the spherical model with the same range in the three experimental semivariograms. This is very important, and the model adjustment is done simultaneously in the three semivariograms. Therefore, this is quite restrictive, and for this reason, in many cases, the Co-kriging model cannot be applied because the same model cannot be properly adjusted to the three experimental semivariograms, the two directs and the cross. This is the major limitation of the linear co-regionalization model. With the Co-kriging model in hand, we will create the grid for the interpolation. Next, we will create the interpolation based on kriging and the interpolation based on Co-kriging. Later, we will undo the transformation to obtain the chloride values back on the original scale. And the last thing we will do is the leave one out cross-validation. We will do it for the kriging method and we will do it for the Co-kriging method. Then we can compare both results and see how, in this particular case, using Co-kriging significantly improve the final prediction results of the salt chlorides levels. Now we will proceed to create the practical exercise where we will see how to create all these graphs, how to analyze the data, how to properly run the scripts, and how to interpret the final results. For our first step, we will load the dataset into QGIS. As we mentioned in the introduction, we have two datasets, one of which is the field samples, which is this dataset we have in CSV format to make it possible to load it into QGIS. In this dataset, we have a total of 134 samples. And what we have in this data table? Well, we have a unique identifier that goes from 1 to 134. We have the X and Y coordinates in UTM, in meters, and then we have the variable, which in this case is the auxiliary variable, which is the conductivity measured in millisiemens per meter with the field instrumentation at a depth of 30 centimeters. In the other dataset, designated with the name lab samples, we have the samples that we have supposedly sent to the laboratory. In this case, we have also a unique identifier, and in this case, it goes from 135 to 254, and in this case we have 120 samples. We also have the variables associated with the X and Y coordinates, which are UTM in meters. Then we have the chloride concentration in milligrams per kilogram, the conductivity measured in the laboratory in millisiemens per meter, and the conductivity measured in the field in millisiemens per meter with the field instrumentation. For these three variables, the samples or the results have been taken at a depth of 30 centimeters. These two variables are assumed to have been measured in the laboratory, and this variable is the one that we have measured in the field, and it is the link between this dataset and the other dataset. So, as we mentioned in the introduction, for the field measurement conductivity, we have a total of 254 samples, which are these 120 samples plus the other 134 samples corresponding to this dataset. As these two files are in CSV format, we can load them directly into QGIS. So we select this option here, we select the limited test, then we select the file which I have on my desktop, and it is in the folder dataset. So first I will add the field data, which is this file, and I have to make sure I have this CSV format option selected. Next, I have to select the X and Y within my data table. Next, the coordinate systems, which in this case, the code is 32613, corresponding to the WGS 84 UTM Zone 13 North. So I select this option and now I can load my data. Now I can close this here, and this is supposed to be the samples that I have taken in the field, which are separated by 400 meters each sample. In this case, it is a systematic sampling. Next, I will load the data from the samples that we have been sent to the laboratory, which is the lab samples. We will do the same thing we have done with the other one. Make sure that we have this option selected and make sure that we also select this one. They are coordinate points. Select the X and Y in the data table, and the coordinate systems in this case is the code 32613. Then add and close. For this second case, the samples are distributed in a completely random manner. The sampling has been random, unlikely the other one that has been systematic. Keep in mind that if you want to download this data, it is easy to do so from the website. Simply click on the 4 course of Geostatistics, then select Start Learning, find the lesson you are interested in. For this example, let's use the lesson 4, the second part of the kriging with external drift. Once you have selected the lesson, scroll down and you will see the exercise file section. This is where you can download scripts, datasets, and any other useful materials that I have included for this particular lesson. Next, we are going to add a perimeter to the investigation zone. In this case, it is going to be a vector file, which I have here already prepared in shape files, and it is designated as the perimeter. So we can open it, add it, and close it. We can add some transparency to it. We go here, select this option, and make it transparent. Let's make the line a little bit thicker, 0.5, and this type. Apply and OK. Now we can also add a satellite imagery as a background, which we can obtain through Google Satellites. At this point, and as a very important note, I would like to emphasize that the data set, both the laboratory and field samples, are no real samples. They have been simulated from statistical models and other real locations where there was indeed chloride contamination. Then with that data and models, we were able to simulate these samples to create an example that is close to the reality as possible. Therefore, this set of data is not real, it is just simulations, and the location we have taken is no real location either. I don't actually know if there are chlorides here or not. We just took this location to add more realism to the practical exercise. It is important to note that these samples are not real and the location was taken randomly. We just took any location to create a representation of a practical exercise. In fact, getting data associated with contaminated soils that is completely accessible and free, it is very, very difficult. There are barely any data set, and people or companies, they don't want to release that type of information because soil pollution, it's a very sensitive issue. So getting this type of data to do practical exercise is an impossible task. In the end, what we have to do is generate fake data, make simulations, and work with these data that are somewhat close to the reality, but not real data. Now we are going to load a third data set in which we will have all the field samples, those that are in the lab samples file and those that are in the field sample file. This dataset is the third one, designated as field and lab samples. So here we have going to add a new layer. It will be a delimited test layer, and it will be this file that I have already indicated. It is also in CSV format, so it can be opened with QGIS. We select all the parameters, we see that everything is correct, add it, and close it. So here, if we uncheck this and this, what we have here are all the data that have the measurement of the conductivity measured in millisiemens per meter with the field instrumentation. They are 254 samples in total, which is what you can see in the attribute table, a single variable, which is the conductivity measured with the field instrumentation for 254 samples. These samples are the sum of the two data sets. Now, what we are going to do is export this file, the lab samples and the field samples, as a shapefile. So what we're going to do is right-click the mouse, export, save feature as, and here we select that we want a shapefile. The name of the file will be the same. We are going to save it in folder number 5, this one here, in shapefile, and we are going to put the name field and lab samples. I put an underscore because I don't want to put strange characters, because sometimes if you put strange characters, the integration of R with QGIS doesn't work well. So it is better to avoid using strange characters like the symbol of "and" in English that is pretty commonly used. Alright, let's save it. The coordinate system is set up correctly and the other parameters are in place, so we can go ahead and press OK. Now our data is in a shapefile format. If you go to properties, you will see that the storage format is listed as the limited test. But if we take a look at the other file we created, we can see in the information section that the storage is an SRS file. So we will do the same thing for the lab samples and for the field samples, but I will speed up the video. Now we can remove the delimited test file. So we will remove the layer, then we'll also remove this layer. If it is delimited test, double check. Yes, it is. So well, remove it. We will remove, I think, is this one. Let me check. Yes, it is. So we can remove this one as well. Now we have all three sets of data in shapefile format. In the end, we want to work with shapefiles because our R scripts integrated in QGIS works better. And if we have shapefiles, we can make all the modifications we want to the attribute tables, and the information will be directly added to the shapefile. Next up, we will analyze data distribution using script number 6 from the lesson 5 of the first Geostatistics course. This script, called histogram.com/bins, can be opened by double-clicking it. First, we will work with the laboratory samples and select the concentration of chlorides as the parameter. For the x-axis label, we will add chloride concentration in milligrams per kilogram, and for the y-axis label, we'll add number of samples. The title of the graph will be histogram of chloride concentration, and for the subtitle, we will add raw data. The minimum value found in the laboratory samples attribute table. If we go to the attribute table for the laboratory samples, we can find the minimum and the maximum values for chloride concentration. We will add these values here, and if we want to save the graph, you can add the link or select the folder where you want to save the image of the histogram. I will add all these fields, but I will fast forward the video. To add the minimum value, as I mentioned earlier, we go to the attribute table, select the minimum value, copy the cell content, and paste it here. Then we do the same for the maximum value. Select the maximum value in the attribute table, copy the cell content, and paste it here. For the number of bins, we can use the calculator. We can take the square root of the total number of samples, which in this case are 120, and the square root of 120 is approximately 11. This will be the number of bins we add to display in the histogram. I made a small modification to the original script. I will show you these modifications in case you want to change it. The only thing I added is this line here to allow us to directly add the number of bins without having to do any calculation with the calculator. Previously, we have to add an interval, but I have modified it to make the script more straightforward and getting the results we want in the histogram. Now let's run the results. Keep in mind that in this case, what we are seeing is not this data, but it is the data behind it, meaning the green samples. So now we can double-click to view the graph and zoom in on the graph. So in the end, here we have the concentration of chlorides in milligrams per kilogram, and here we have the number of samples. In each bin, the number of samples appears at the top. And as we can see in this case, the distribution is quite normal. But to get more reliable results, we can add a box plot to this graph, where we will also see the mean and the median of the data. So to do that, we'll use a different script, which in this case will be number 13, corresponding to the lesson number 6 of the first Geostatistics course. And I'm going to select the lab samples. In fact, I am going to copy everything because it will be the same here. The parameter is the concentration of chlorides. Then for the label on the x-axis, I will copy and paste it. I will do the same for the y-axis labels and the same for the graph title. But here I will add histogram and box plot. The subtitle will be the same, which is raw data, the data without any transformation. The values here are the same, which is 14 and 387. This is the concentration of chlorides in milligrams per kilogram, and the number of bins is the same, 11. So now we can run this. In this script, I apply the same modifications as in the previous one with respect to the original. Let me show you. As you can see here, as in the previous case, we previously had to add an interval, but now we directly add the number of bins. So now we can run this, double click to open it. Now we can zoom in on the image and we can perform a data distribution analysis. As you can see, the box is located approximately in the middle of the histogram. Then the mean and the median are very close. The graph is overall quite symmetrical and we don't have any outlier values. So all this information indicates that the distribution is fairly close to the normal, also known as a Gaussian distribution. Then The case of data having a distribution close to the normal or normal, it is important for the creation of the experimental semivariogram, because in this case, the mean and the median values are representatives of the data set. However, if we have a histogram that didn't quite present a normal distribution, it couldn't be a problem either, because the case of the formula for creating the experimental semivariogram doesn't require the data to be parametric. It doesn't require the data to have a normal distribution. However, if we have a normal distribution of the data, the experimental semivariogram will be better. It will fit better to the interpretation of those data. But if it is not possible, well, the experimental semivariogram can still be performed, but the results obtained would not be as good as if we have data that was close to a normal distribution. It should be mentioned that here we are talking about Co-kriging analysis. So in this type of interpolation technique, the model is more restrictive. This forces us to have the different direct experimental semivariograms present a normal distribution or closer to the normal due to the model's restriction. We will see this later. Now, the next step is to look at the distribution associated with the electroconductivity measured with the field instrumentation. So to do that, we are going to use the same histogram, but here changing the variable. In this case, they will be the field and lab samples, which will be this. The variable of interest is the electroconductivity measured with the field instrumentation. Here we will have to change the label to electroconductivity in millisiemens per meter. Here we will have to change the title indicating that it is the electroconductivity, and here we'll have to change all these intervals and the number of bins. In this case, as we have already said, let me show you with the calculator. What we have are 254 samples. 254, the square root is about 16 bins. That's the value we want to add here, 16 bins. Then for the maximum and minimum values, we have to look at it here in the attribute table. The minimum value is 12 and the maximum value is 198. So here 12 and here 198. I'm now going to change the labels, but I'm going to fast forward the video. I have already added all the labels and now I'm ready to run this script. So press here and double click to open it. Then we can enlarge the image. As we can see in this case, the histogram seems to be a bit asymmetric, where most of the values are concentrated in this area of the graph. Then to see if there is any type of irregularity in the data distribution, we can make another histogram, but with the box plot, to know where is the mean value and the median value, and also if the box is located at the center of the histogram or is just on one side, indicating the asymmetry of the histogram. So for that, we are going to run the script number 13 again, but in this case for the electrical conductivity, which is going to be this script right here. And we are going to do as before, copy and paste all the things. So here we have to select a different layer, which is the field and lab samples. It is this layer right here. The parameter is this one. Here we are going to copy this and paste it. Copy and paste it here. The number of samples is the same, but the title here is going to be electrical conductivity. This is the same. This is the same. This changed because the minimum is 12 and the maximum is 198. And the number of bins also changed because the number of samples we have is practically double. So now we can run this script and double-click to open it. We can enlarge it, and as we suspected, we have an asymmetrical histogram where the box is positioned more towards to the left, and the mean and the median are not together. So in this case, it becomes a problem because when I try to perform the Co-kriging, what I saw is that when I'm using this data, this one for the chloride concentration and this one for the electrical conductivity, the model doesn't fit really well on the data. I had a good fit for the chlorides and the cross semivariogram, but I didn't get a good model for the experimental semivariogram of conductivity. Remember that the model fit has to be done simultaneously for the three semivariograms, for the chloride, for the conductivity, and for the cross between the chlorides and conductivity. So if one of these three models doesn't fit well, the results are not good. So I think the problem of not fitting well was due to the distribution of the conductivity data. So for this reason, I decided to make a transformation of the data. So I used the square root to transform the concentration of chlorides and to transform the conductivity. That's what we are going to see next. We are going to transform the data directly in QGIS. We close all these first. Now we are going to QGIS and we are going to the attribute table of the laboratory samples. Then here we press the pencil to start the addition. We go to the field calculator and we create a new field. In this case, it will be the square root of the concentration of chlorides. So we put here decimal number, that's fine. We go to the math and we select the square root. So we go here and we select the field we want, which in this case is the chloride concentration. We close it and OK. Then now here a new field has been created, which is the square root of the chloride concentration of this variable here. Then we close the editing. It is important to close the editing because otherwise the script wouldn't work properly, and also it is important to keep here a simple name without strange characters so that it works well with R. Now we will do the same for the laboratory and field samples together. We open the attribute table, press the pen to start the editing, open the field calculator, and here we use the same variable, the square root, for the field conductivity, decimal number, and we go back to the math and select the square root here. We select the variable we want, which is the conductivity measured in the field. Close the parentheses, and now we can create this new field. Close the pencil, close the editing, so it works well with the script, and save it. Now we can close this, and now we can create the histogram. So this is the same field lab samples layer, but now the variable is the square root of the field measured conductivity. So here we can add that, it is the square root. This is the same, this is the same. Here will be the transformed data, and we can add that, it is a square root. Then the maximum and the minimum values now change. So we open the attribute table, go to the new variable and select this value, which is the minimum value, and paste it here. Then we go back to the attribute table and now we select the maximum value and paste it here. The number of bins stays the same, and now we can run this script. We double click to open it and we can increase the chart. Now, as you can see, the chart is much more symmetrical compared to the previous one where the box was more to the left. In this case, the box stays more in the center and the median and the mean values are closer together. Then, with all this information, we can say that now the data of the field measured electrical conductivity follows a more normal distribution compared to the results we had before with the untransformed data. In this case, this distribution is much better for the Co-kriging application in this case. Now we are going to see the transform histogram for the chloride concentration. So we go here, and here we have to change the parameters. We have to select the layer associated with the laboratory samples. The parameter we want is the square root of the chloride concentration. And here we are going to change the labels, but I'm going to fast forward the video. Remember that here the number of bins is smaller, it is 11. So I have added all the labels, and now we can run the histogram for the chlorides. Double click to open it, and we can increase the graph. It is interesting to see how in this case the data distribution worsens with the transformation. If we compare chloride concentrations with the square root transformation with the untransformed data, we see that the transformation worsens the data distribution, pushing the mean and the median a little bit farther to the right, as well as the box. Now the box is not centered in the histogram, and the histogram is slightly asymmetrical. This is the original data without transformation, and this is the transformed data. However, the worsenings that occur in this case is not as bad as the improvement that occurs in the electroconductivity. In the electroconductivity, we go from this to this, where the improvement is quite significant. But in the chloride case, the worsening is not as marked, because as you can see, for example, the mean, which is the most important value, those more or less stay in the center of the box. And that is important. And the median and the mean are not too separated. So if you wonder why not keep, for example, chloride concentration without transformation and the transform electroconductivity, it is because we want to keep the scale of the values. Now, when we compare the field electroconductivity with the chloride concentration, we want this association to present a linear relationship. But if we keep, for example, the chloride concentration without transformation and the transform electroconductivity, we will see that the relation is not linear, but is quadratic. So in that sense, we want to keep the scale of the values so that when we correlate the parameters, we don't not have any problem later with the Co-kriging. So for this exercise, we will use the transform data. It is the student task, verify how the experimental semivariogram can be made with the raw data, but then the model adjustment doesn't fit really well when using the linear model of correctionalization. We are not going to see this in this exercise, but it remains as a part of the student work to make this verification. Now the next step is to check that the electrical conductivity measured in the laboratory is equivalent to the electrical conductivity measured with the field instrumentation. So we are going to use the values we have in this data set. We will use the electrical conductivity measured in the lab and the electrical conductivity measured in the field. These two parameters must be highly correlated, so we can know if the model is well calibrated or not. To do this, we will use script number 46 from the lesson 9 of the third Geostatistics course, and is this script we have here, feature space linear correlation, and the parameter we will calculate is the Pearson's coefficient. Double click to open it. Here we select the layer of interest. which is the sample lab. The X variable will be the electrical conductivity measured in the laboratory, and the variable for the Y will be the electrical conductivity measured in the field. Now I am going to introduce all the labels for the X-axis and for the Y-axis. The title of the chart will be Correlation between Conductivity. The subtitle will be Raw Data. And here, if you want to save the file, you can enter a link or select the folder where you want to save the file. Once all the labels has been added, we can run the script. As you can see in this script, we obtain the value of the Pearson's coefficient, which in that case is 0.99, indicating a very high correlation. The perfect case will be 1, and here it is close to 1. That is, the correlation, it is very high. We can double-click to open the chart. And as you can see, the electroconductivity measured in the laboratory against the electroconductivity measured in the field, they practically form a straight line. In this case, using the Pearson's coefficient is ideal because, as we can see, the relationship is completely linear. In the case that it was not a very linear relationship, we will have to use the Spearman coefficient. This has already been explained in the second lesson of the second Geostatistics course. If you want to learn a little bit more about how to use Pearson's or Spearman, I invite you to view that lesson. As in this case, the value of electrical conductivity in the laboratory are the same as the values obtained with the field instrumentation, we do not have to make any change to the values measured in the field, because we already know that the results of the measurements made in the field are good and are equivalent to the results obtained in the laboratory. Then we can conclude that the results that we measure in the field samples in this data set, in the data set related with the field samples, are also good, because the results that we get from the lab provide the same results. The next step will be to look for a correlation between chloride concentration and field measured conductivity. So to do that, we will use the same script, but in this case, we will change the variables. For the X variable, what we want is the chloride concentration, and for the Y variable, what we want is the field measured conductivity. So all we have to do here is change this variable, chloride concentration measured in milligrams per kilogram. So this stays the same, but it is going to be the square root 2, and here the title will be a square root of the field measured conductivity and chloride concentration. So this is the data transformed by the square root. Now we can already run this script and see the relation between the two variables. As we can see in this case, the Pearson's coefficient value is 0.98. Once again, this indicates a very high correlation. Remember that the ideal value will be 1. With a value of 1, we will have a perfect relationship. Here, the relationship is almost perfect. When we open the graph, we can see that we can plot a nearly 45-degree perfect line with this data. This indicates a very high correlation between chlorides and electroconductivity in the field, indicating that we can use electroconductivity as an auxiliary variable to have a better prediction of the chloride concentration. Now we can observe what happens if, for example, instead of adding the concentration with the square root transformation, we add the chloride concentration without any transformation against the square root transformation of the electrical conductivity. I am going to put all the labels. I'm just going to change the variable here. This is wrongly placed here because what we should add here is the square root. Here we have done something wrong. We have to modify the attribute table. So we have to go to the field samples, go to the attribute table, add a new attribute that will be the square root of the electroconductivity measured in the field. Then we have to press the pencil and add a new field, which will be the square root of the electrical conductivity measured in the field. Remember not to leave any space. So here we want it to be a decimal number. We go to the math, add the square root. We go to the field and add here the electroconductivity measured in the field. Then press OK, close the edition and save. Double click to open it again. So it is the lab samples. Here it will be the square root of the chloride concentration, the square root of the electroconductivity measured in the field. So I'm going to add the labels, but I'm going to fast forward the video. Okay, I have entered all the data correctly. Now we have the square root of the chlorides, the square root of the electroconductivity. I have put the labels, the title, and we can run this script again. In fact, it will be very similar to the other because, after all, the same variables are used for the correlation. It will be the same, but in this case, both transform data. As you can see, the correlation is the same. We double-click, we can make this graph bigger, and if we compare it with the other, it is pretty much the same. It changed a little bit the location of the points, but again, the line we can draw here is a 45 degrees line, indicating a perfect correlation between the two variables. So here, if what we do is use a transformed data and data without transformation, let's assume we use the chloride without any transformation, because as we saw before, the histogram shows a better distribution. I changed the labels here, and we can run this script. Now, what we can see in that, the correlation is not linear like it was before. Here the correlation is linear, here the correlation is not linear. It is of a quadratic type. We see that it forms a kind of curve and it is quadratic. So to avoid this kind of situation, when we make the transformation, we make the transformation to both variables. So we maintain the linear relationship between the variables. This helps a lot in adjusting the linear model of correlationalization. As the name indicates, the variables has to show a linear relationship. In the end, to avoid any kind of problem, we adjust the model to a linear correlation. Later, what we want to do is to check if the chloride concentration shows any trend on the data. So to do that, we will use the script number 31 from the lesson number 4 of the second Geostatistics course. We select the layer of interest, which is the lab samples. Here, the interest variable, which in this case will be the square root of the chloride concentration. For the y-axis will be the x-coordinates. So now I will add the labels, but I will skip the video quickly. I have already added all the labels. As you can see, for the x-axis, we have the square root of the chloride concentration. For the y label, what we have are the x-coordinates, which are in UTM in meters. The title of the graph is Analysis of the Trend in the X-coordinates, and the subtitle is Data Transform with the Square Root. We can run this script and double-clicking to open the graph. The script creates a scatter plot of the square root of chloride concentrations against the X-coordinates in meters. The purpose is to fit different types of polynomial to the data. However, in this case, we can observe that there is no trend and the data is randomly distributed. If there were a trend in the data, we will see how the polynomials fit to that trend. Due to the high dispersion of the data, there is no clear trend. Nevertheless, the script always fits a polynomial to the data using the ordinary least squares criterion, but this is not indicative of the presence of a trend in the data. Now we can perform the same analysis using the y-coordinates instead of the x-coordinates. We will change x to y in the script, and also change the title to reflect this. After running the script, we can see the new graph. In this case, it is also not clear that there is a trend in the data. Again, the data is randomly distributed, and the best fitted model is shown in the graph. However, the polynomials are not truly showing any trend because the data is randomly distributed. Therefore, in this case, we can consider that there is no trend in either the x or y direction. In this case, we have decided to use scatter plots and polynomial fitting to identify trends in the data. However, as we have explained throughout the courses, there are different types of tools that we can use. For example, we could use a graduated map where we project the concentrations with different colors to see if there is a trend in the data. This would be a more spatial analysis that we have used, which ultimately is a two-dimensional graph. Similarly, we could use a bubble map where the diameter of the bubble is large according to the concentration of chlorides. This analysis could be represented on a map and could be a more three-dimensional representation. Another analysis could be the execution of a scatter plot of the data in 3 dimensions to see if there is any type of trend. In this exercise, trend analysis with scatter plots in 2 dimensions is sufficient, and there is no need to create more graphs or maps to identify the trend. Throughout these geostatistics courses, not only in the 4th course, but also in the 1st, 2nd, and 3rd, a whole series of tools has been offered that can be used for geostatistical analysis. In this lesson, we are not using all the tools. We are using only a few of them, because if we wanted to use all of them, the video tutorial will be extremely long. For example, in the topic of analyzing data distribution, could be also have used the QQ plot or numerically quantify the normality of the data with Kolmogorov-Smirnov or Shapiro-Wilk test analysis, but we didn't, because using the histogram and the box plot was enough in this case to analyze the data distribution. So we are not using all the things that have been taught throughout the courses. We are only using a few of them, which are enough to successfully perform the Co-kriging interpolation. However, when you are performing geostatistical analysis, you can add more tools or processes to quantify the values. However, in this case, we are using the ones we are showing in this lesson. That doesn't mean they are the only tools you can use. There are more tools, but in this specific case, we are using these, which from my point of view are sufficient to perform the practical exercise. It is possible that more tools could be used to improve the results, but that would require more analysis time. Now it is time to consider why we have done the trend analysis. The goal is to truly know that the data doesn't exhibit a trend, because in the case that a trend exists, it will indicate that the data doesn't exhibit stationarity. So if the data doesn't exhibit stationarity, we cannot apply kriging. Therefore, in the case that a trend does exist, we will first have to remove that trend from the data and work with the residual values. However, if that were the case, then we wouldn't be doing ordinary co-kriging. Instead, we will be doing universal co-kriging, co-kriging with external drift, or co-kriging with regression. This is where remove the trend and work with the residual values. However, this is not the case for this practical exercise, where the data doesn't exhibit a trend and stationarity exists. Next, we are going to see how we can create the omnidirectional semivariogram cloud. This data is also interesting to see if there is any trend in the data, any clustering, or any outliers. To do this, we are going to use the script number 1 from the second lesson of the third Geostatistics course. Double-click to open it, then we are going to add the data. We want to work first with this layer, so we are going to select the variable of interest, which in this case is the square root of the chloride concentrations. For the cutoff, we want the total extent. The longest extent in this case is about 6 kilometers. So I am going to add 6 kilometers here. Let me double check exactly. We can select this tool and measure the longest extent between two samples. As you can see here, for example, in this case it's about 5,500 meters and here 5,000. So roughly 6,000 meters. That is the one we want to add here, 6,000 meters. The label for the x-axis will be the distance, the lag in meters. The y value will be the semivariance value of the square root of the chloride concentration. The title of the graph will be Semivariogram cloud for the square root of the chloride concentration. And the subtitle will be the transformed data. Now I am going to add the labels, but I am going to fast forward the video. I have added all the labels and now I can run this script. Double-click to open it. We can zoom in on this image. Here we have the range of distance in meters, commonly known as a lag. And here we have the square root of the chloride concentrations, semivariance. There is no discernible trend, outlier values, or clusters in this semivariogram cloud. A cluster will be a group of points separated from the main semivariogram cloud, but we cannot observe any cluster in this case. If we observe trends, outliers, or clusters, we will have to analyze those data independently to see if they affect the experimental semivariogram in general. In this case, since we don't have any of those issues, the semivariogram cloud is appropriate and we can proceed to the next step. I noticed that we have a point here that is nearly 6,000 meters away. Before, when I looked at the distance, I saw that the maximum distance was approximately 5,500 meters, which is what I have calculated from here to here. However, I now realize that we have a point almost 6,000 meters away, which must be the distance from this point to this point here, which, as you can see, is 7,000 meters. This will indicate that we have more points at longer distance. So we could even extend this distance to 7,000 meters. Here we can see what happens when we increase the distance. Double-click to open it. However, there are no samples beyond 6,000 meters. I realize that the issue is that we are measuring chloride concentrations, and I was taking the distance from the field samples. So I would have to remove this and put the samples here. Then I can measure the distance here in this map. The maximum distance should be from this point to this point here, which is approximately 6,000 meters, and what we saw in the semivariogram cloud. In this graph, 6,000 meters is the maximum distance, and that is why even when we increase it to 7,000 meters no longer pair of samples were added to the semivariogram cloud, since the pair with the greatest lag is around 6,000 meters. So now we can do the same, but instead of using chloride concentrations, we want to use the field electroconductivity. In this data set, we want to add the square root of the electroconductivity measured at the field. Here we want to set an extension of 7,000 meters because we now have pair of samples that are that distance. If we remove this and this, we will work with this, and here we see that we have this maximum distance, around 7,000 meters. So we change the distance here, which is good, and the semivariance for the electrical conductivity values of the field, and I am going to change these two here, and the unit is millisiemens per meter. So we need to change it here too, and that's it. Now we can run this script. Double click to open it. We can make the graph bigger. As you can see, we have this value here, which is close to 7,000. In this case, the point cloud is much denser because the number of samples we have is twice that of the chlorides. So that is shown with a higher point density. Here, we doesn't see any trend, we doesn't see any clusters, and we don't see outliers. So, as everything seems correct, we can move on the creation of the experimental omnidirectional semivariogram. I would like to point out that we are not going to work with specific directions for the experimental semivariogram because the number of samples we have for the chloride concentrations is only 120. So the experimental semivariogram would not be robust if we wanted to do it in a specific direction. Remember that the topic of the directional semivariogram was already explained in the lessons 3 and 4 of the third Geostatistics course, where we talk about the directional point cloud and also the directional experimental semivariogram. In those lessons, we already saw that the number of samples that falls within the bin for the analysis depends on the tolerance angle. That tolerance angle can be quite restrictive for the number of samples. So in those places where we don't have high sample density, it can generate very weak directional semivariograms, which can create false structures in the data. Therefore, in this case, we are only going to work with omnidirectional semivariograms. In order to have a robust semivariogram, I have realized that for the values of the electrical conductivity for the semivariogram point cloud, I didn't specify that it is the value of the square root, and I also didn't specify it here. But understand that this is based on the data transformation. I should be added here, even though it has already been added here, indicating that the transformation is the square root. But the labels should be added correctly in the script. Now, what we are going to do is the experimental omnidirectional semivariogram. So let's add the layer we are interested in here. First, it is going to be the lab samples because we are going to work first with the square root of chloride concentration. We are going to use the same cutoff as before, which was 6,000 meters, and for the lag we can start with a general value of 600 meters. The label for the x-axis will be the lag in meters, and the label for the y-axis will be the semivariance of the square root of chloride concentration in milligrams per kilograms. The title will be the experimental semivariogram of the square root of chloride concentration, and the subtitle will be the transform of the square root. I am going to add all these labels, but I am going to fast forward the video. Now that I have added all the labels, we can run the script. Double click to open it. Let's make the graph bigger. Remember that this script is part of the lesson 4 of the 3rd Geostatistics course. Also remember that if we want to know the maximum distance between two samples, we can use the default algorithm in QGIS, which is the distance matrix. If you put matrix distance here, it is this one here. Then double click, select the layer we want to analyze. In this case, it is the lab samples. Select the variable, which in this case can be, for example, the concentration of chlorides. And for the target point layer, we can leave it as the same layer because we will be working on the same layer. And again, select the concentration of chlorides. So now we run it, and it will generate a file, which is this one here, the distance matrix. If we open the attribute table, we can see the minimum and maximum distance between pair of samples. In this case, since we have put the chloride concentration, we cannot see which samples they are. But if instead of putting the concentrations, we select, for example, the ID, in both cases, and run the script again, we can remove this layer. Now we can see which sample it is. So we can open the attribute table again, and as we can see, it calculates the distance between two samples in both directions, from sample 179 to 211, and from sample 211 to 179. Which is why we have the same values twice, because it is calculated in both directions. So the minimum distance between two samples in this data set, in the lab samples, is 65.86 meters, and the maximum distance is 5,964.2 meters. These distances are reflected in the graph. When we have created the Semivariogram cloud, in this case, it would be this sample here, which would be the pair of points that consists of samples 163 and 228. So we can use the distance matrix to select the cutoff for both the Semivariogram cloud and to create the experimental omnidirectional Semivariogram. We want to create the experimental Semivariogram with the entire extent to see if there is any trend in the data. In this case, we can see that the experimental Semivariogram starts to increase and stabilizes at a certain point. At this point, we would say that this omnidirectional experimental Semivariogram is reaching the seal. When we reach the seal and the Semivariogram stabilizes, we can say that we have reached the range. The distance from 0 to the range would be the part of the experimental Semivariogram that shows a spatial correlation, and it is the part that we are interested in to fit the model. With a general experimental Semivariogram like this, we can see different types of information. First, there is no trend in the data. Second, that the Semivariogram we have in this case is pretty robust, because we have 376 pair of samples in the first log, and in the next one we have 1000, indicating that the Semivariogram is very robust. We can also see how the experimental Semivariogram behaves throughout the entire research area, as well as having an instantaneous view of the spatial structure of the data. Later, we will make the same graph, but only focusing on the part of the spatial correlation of the data, where we can see more clearly if there is an aggregate effect and what the seal and range of this data could be. Now, the next thing we are going to do is to analyze the omnidirectional experimental Semivariogram for the field measure electroconductivity. So we are going to use the same script, but we are going to change the layer, because in this case we are going to work with the field and lab samples together. Now this one is for the matrix. Well, we can also calculate the matrix here to see the distance. So we select the field and lab samples together, and we can run this script. Now we can also see what is the minimum distance and the maximum distance between two samples. In that data set, the minimum distance is 18.60 meters, and the maximum distance is between samples 1 and 134, which is 6,790.68 meters. So now with the script for the omnidirectional experimental semivariogram, we can input that data. We want to analyze the layer that has the field and lab samples together. We want to analyze, in this case, the field measured electroconductivity using the instrumentation, which are the transformed data. The cutoff is 7,000 meters. The lag distance, in this case, to have a general idea of the data structure, we can put, for example, 600 or 700. So we will leave it at 600 as in the other case. So this label changed because now we look at the semivariance of the conductivity measured in millisiemens per meter. And the graph title also changed to conductivity. The other data are the same, and now we can run this script. In the pop-up windows, I have written a script to print various data. We can see the number of lags we have in this experimental omnidirectional semivariogram, a total of 12 lags. Then we have the total number of samples for each lag. For example, in lag number 1, we have 1,642 pair of samples, and in lag number 12, we have a single pair of samples. In lag number 11, we have 25 pair of samples. Additionally, we have the value associated with the distance of each lag. For example, for the first lag, it is a distance of 419.6 meters. And we also have the value of the gamma, which is the semivariance. For this first lag, the semivariance has a value of 4.38. All of this information can be seen in the graph. Double-click to open and make it larger. We have the first lag, second lag, third lag, and so on. Next, to each lag, we have the number of pair of samples. For example, in the lag number 11, we have 25 pair of samples, and the distance of this lag is 6,242.6 meters. We can see this distance on the graph. In this graph here, this lag is located at that distance. And what is the value of the semivariance? Well, it is this value here that doesn't quite reach 15. So we can also see that here, the value of the semivariance is, in this case, 14.54. Additionally, we have other variables such as horizontal and vertical direction, which are marked as 0 here. The horizontal direction will be if we have some kind of direction in the experimental semivariogram, which is not our case because we are working with the omnidirectional semivariogram. And then in the case of the vertical direction, it is if we have applied some angle for the calculation of the experimental semivariogram, such as some deep angle. In this case, as we can see in the graph, the omnidirectional experimental semivariogram is more robust than in the previous case because we have more pair of samples. This is normal because the number of samples we have for the field conductivity measured with instrumentation is practically double the samples we have for the chlorides. That's why we have around 1,000 pair of samples here and around 4,000. Even in some cases 5,000 pair of samples here. In this case, there doesn't seem to be any trend also. The semivariogram stabilizes around this point, which is the value of the seal, and the range is reached at approximately this distance. we see this more clearly when we zoom in on the correlation area of the graph. The fact that in this graph, in the area where we have the maximum extent, the values of the lags start to raise up, it's not important because the number of sample pairs is very small, and also because this area of the graph, it's not where the correlation is present. The area that presents the correlation and where we will fit the model is this area of the graph. So what happens here is not really important. Now, the next step is to focus on the correlation area of the graph. So what we are going to do is zoom in on this area of the graph. This is very simple. All we have to do is go back to the script, and instead of putting a cutoff of 7,000 meters, we will put a cutoff of, for example, 1,500 meters and the lags of 150 meters. Now we can run this script. Then in the pop-up windows, all the data corresponding to the new experimental semivariogram is printed, which we will now see on this graph. Double-click to open the graph and zoom in. In this case, we have the experimental omnidirectional semivariogram for electrical conductivity. It is clear that the data presents a structure. We have an increase in the semivariogram, which stabilizes at this point. We could say that the negative effect we have is small, of the order of 2 units, and the seal is reached at an approximately high of 7 units. The rate should be oscillating between 1,250 and 1,300 meters. On the other hand, we can observe that when we reduce the lag distance, remember that in this case the lag is 150 meters, the number of sample pairs we have for each lag is smaller, because with a smaller lag we capture fewer samples, while in the previous case the lag was 600 meters and the number of sample pairs for each lag was much larger. Therefore, the semivariogram centered in the correlation area is less robust because the number of sample pairs per lag is smaller. However, a semivariogram with more than 100 sample pairs per lag is sufficient to be representative of the data. In this case, the first lag has 65 sample pairs, which is not much, but is sufficient to be representative of the data at that distance. Obviously, the more sample pairs per lag, the more robust the semivariogram will be. It is worth mentioning that the number of lags we add is important, as well as the cutoff, because if we set a longer cutoff, we will potentially have more lags, and these lags are used to adjust the model. Subsequently, the values obtained with the model will be used to perform the kriging. So, if we have more lags, the model will have more points to adjust. But if we set points that are outside the correlation zone, we will be adjusting the model with lags that do not have a spatial correlation. Therefore, we want to make sure that the cutoff reaches approximately where we have the range. We should not adjust the model with those outside the range, as those don't have a spatial correlation. For that reason, I decided to set a cutoff distance of approximately 1,500 meters. In this specific case, the model will be adjusted using all these 10 lags, which are sufficient to properly adjust the model. If you find that you have many pairs of samples in each lag and you want to have shorter lags to obtain more points to adjust the model, that will ultimately depend on your data. In this case, 10 lags are sufficient to adjust the model properly. Keep in mind that all of these lags we are using are approximately within the correlation zone of the experimental semivariogram. So you have to consider that every time you change the number of lags or the cutoff length, you will have different data. This will give you a different nugget, a different seal, and a different range, because the model is adjusting according to the number of lags on the graph. So, before adjusting the model, consider the number of lags and cutoff you want to use. Now we will create the same plot, but for chloride concentration. So we can close this one and select another layer, the lab samples. And the parameter we want to analyze is the square root of the chloride concentration. The cutoff is the same, 1,500 meters. The lag distance is the same, 150 meters. The parameter names and the units change because we are now looking at chloride concentration in milligrams per kilogram. Now we can run the script. Double click to open it and then expand the graph. As we can see, the data also shows a structure with a seal, range, and Nager effect. However, compared to the previous semivariogram, there are few pair of samples in each lag. This is because, in this case of the chloride concentration, we have only about the half as many samples as we did for the electrical conductivity measure in the field. Next, we will fit a model to this semivariogram. To do this, we will use the script number 19 from the lesson 5 of the third Geostatistics course. Let's go to R, see the script we have saved, and select script number 19, which is designated as Model Semivariogram Omnidirectional. So now we are going to close these two and select the layer of interest. We will start with the concentration of chlorides, lab samples, and the parameter will be the square root of the concentration of chlorides. For the cutoff, we'll use the same value, 1,500 meters, and the lag will also be the same, 150 meters, just like we did with the experimental semivariogram. Now we have to input values for the seal, the model we want to use, the range, and the nugget. These values are approximately, and we need to input them to start the computational process. So for the seal, we will look here, and it will be around 16.5, which is approximately the value. This parameter is not truly the seal, it is the partial seal. And we need to change this because it is an error. If you have followed all the courses, you will know how to edit the script. I am going to show it again for those who don't know how to edit a script. Now I am going to edit the script and I will put partial seal here. Then I am going to copy this and paste it here. Then I will save it, close it, and go back to the script. I will close it again. I hope it has been changed. Number 19, and now we can see that it says partial seal. So again, we want to select the lab samples and the transform concentration of the chlorides. The cutoff we set was 1,500. The lag is 150 meters. And for the partial seal, we will look at the graph. We assume, for example, that the Nager effect will be around 4 units, and the partial seal will be approximately 11 units. These are approximately values. First, we will try the spherical model. The range we set was approximately 1,500 meters, and the Nager effect is approximately 4. We need to add the labels for the X and Y axis, the title of the graph, and the subtitle. The label for the X axis will be the lag distance, and the label for the Y axis will be the semivariance for the square root of chloride concentration. The title of the graph can be Experimental Spherical Semivariogram Model, and the subtitle can be Data Transformation, indicating that the data has been transformed with the square root. I will add the labels quickly, and I have decided to put a spherical model for chlorides as a title. Then we can run this script. As you can see, the script is set up to display the results of the data structure in a pop-up windows. we have an Agra effect of 4.26, a partial seal of 12.62, and a range of 1,427.51 meters. You should understand that these values are calculated automatically by the software based on the model that fits the lags in the graph. Next, double-click to open the graph and zoom in to get a better view. Now we can see how the script has fitted the model to the data. You should note that this model is fit to the data based on the weighted least squares, with greater importance given to the lags in the initial zone of the graph, all this zone here, and less weight or importance given to the values located in this zone of the graph, close to the range of the structure. It is important to know that fitting a model to the data is a whole science, and there are many ways to do this process. For this exercise, we have decided to use automatic fitting, letting the software adjust the model automatically. However, this fit can also be done manually. If you want to delve further into the topic of model fitting, I recommend that you take a look at the 5th lesson of the 3rd Geostatistics course, where we discuss the different types of adjustment that can be made. Keep in mind that in the end, fitting the model is a trial and error process, trying different models, adjusting the model to the data, performing cross-validation, and seeing which model offers the best results for the interpolation with kriging. In this exercise, we are not going to go through the whole process, but you have as a reference the lesson 1 of the 4th Geostatistics course, where we apply ordinary kriging, the lesson 5 of the 3rd Geostatistics course, where we was discussing the data modeling, and also the lesson 8 of the 3rd Geostatistics course, where we was talking about the tools for the cross-validation. However, it should be noted that when working with Co-kriging, fitting the model to the data becomes enormously complicated. This is because the model has to be simultaneously fitted to at least 3 experimental semivariograms, 2 direct and 1 cross. To avoid all this complexity and save time in the data analysis, I have decided to use automatic model fitting. In this particular case, I have opted for the spherical model because it usually works better with soil samples, but other authorized models such the Gaussian, exponential, etc. could have been investigated as long as they are models that meet the premises of the linear model of correctionalization. In the end, the time for data analysis will depend on the project budget. The more money available, the more time for the analysis, the more reliable the results. Now, what we need to do is save the information associated with the structure of this data. We need to save the partial seal, the nugget, and the range, because we will use them later. Next, we will fit the model to the electrical conductivity measured with the field instrumentation. So we have to select this layer, and here the square root associated with the transformation of the data for the electrical conductivity measured with the field instrumentation. These values will be the same, and we need to check the values we are going to use for the partial seal in the graph. This graph is for the chlorides, and this one is for the electrical conductivity. So we have a partial seal that is possibly around 5, and an Agra effect that is possibly around 2. We will use a partial seal of 5, leave the model the same, leave the range the same, and use an Agra effect of 2. We will change this for electrical conductivity measured in millisiemens per meter. We will use a spherical model for the electrical conductivity. Then we can run the script. As you can see, the data related to the structure of this model is printed. We have an Agra effect of 1.74, a partial seal of 5.40, and a range of 1,209 meters. Next, we can open the graph and see how the model is automatically fitted to the data. It is important to note that for applying Co-kriging, the model has to be the same for both experimental semivariograms, one from the chlorides and the other one from the electroconductivity. The range also has to be the same for both. The only thing can be varied are the Niagara effect and the partial seal. As you can see, the model is spherical for both variables. The range changed a bit because here we said the range was around 1,400 meters, and here it is 1,200 meters, which is the data we saw earlier. The range is 1,200, and in the other case it was 1,400. Later, we will have to adjust the range to the different variograms to successfully obtain the linear model of co-regionalization and apply Co-kriging. Remember that the range has to be the same in all three semivariograms, the two directs and the cross one. Now that we have the information associated with the structure of the two direct semivariograms, we can calculate the cross one. So let's use the script 47 and 48 from the lesson 9th of the 3rd Geostatistics course. We can close this and first run script number 47. Here we put the target layer, which is the layer that has the main variable, the concentration of chlorides. The auxiliary layer is the one that has the field and lab samples associated with the electroconductivity measured with the field instrumentation. The target variable is the square root of the concentration of chlorides. The auxiliary variable is the square root of the electroconductivity measured with the field instrumentation. We already know that the cutoff is 1,500 meters, and the same for the lag distance of 150 meters. The name of the target variable is chloride. The name of the auxiliary variable is the electroconductivity, and now we can run this script. In the pop-up windows, we have the same data that we were seeing before, but now for the three experimental semivariograms. First, for the cross between chlorides and electroconductivity, followed by the data for the experimental semivariogram of the electroconductivity, and then for the experimental semivariogram of the chlorides. In each case, we have the number of sample pairs we have for each lag, the lag distance, and the value of the semivariance. Double-click to see the graph. In this case, cannot see anything because the y-scale is too small, 0.20. So we have to modify this value to make the graph visible. What is the maximum value we need on the y-axis and on the x-axis? Well, on the x-axis, it will be the range, which is 1,500 meters, and we are already covering it here. But on the y-axis, we can see that in this graph, it is of the order of 20, and in this other one, it is of the order of 7. So we need to leave at least a value of 20. Then we go to the script, select Edit option, and then modify the scale. For the x-axis, from 0 to 1,500 meters. For the y-axis, from 0 to 20. We save the change. This is a limitation of the scale I set to create all the graph with the same scale. But if you want, you can remove this limitation. You can also indicate whether you want to see the number of sample pairs for each lag by putting true, or not see it by putting false. In this case, I left it as a true, so the number of sample pairs for each lag will be visible. Now I can close the windows and go back to the script. Well, it is this script. Now I can run it again. We double-click to open it, and now, as you can see, the graph is already visible. We can zoom in on the image, As you can see, for each lag, we have the number of sample pairs. However, these numbers make it difficult to visualize the model, which is why we are going to change the option for displaying the number of sample pairs. So we can go to edit the script, number 47 again. So we change this option from true to false, save the change, and run the script again. Now the graph is much clearer. We have the direct experimental semivariogram for the electrical conductivity and for chlorides, and the cross semivariogram for both. As you can see, the cross semivariogram presents intermediate values between the semivariogram of electrical conductivity and the semivariogram of chlorides. Now let's take a look at the script number 48, which offers the same information presented in a different way. To make this new graph, we will use the ggplot package of R. So let's go to the script number 48, double-click to open it, input the target layer, which is the lab samples, select the auxiliary layer, which is the field lab samples, input the target variable, the auxiliary variable, the cutoff is 1,500 meters, and the lag distance is 150 meters. Now I will add the labels. Well, I have already added the x-axis label, which is the lag distance in meters, the y-axis label, which is the semivariance. I haven't specified any parameter because in this case we will work with all three semivariograms at the same time. One will show the semivariance of the chlorides, the other one will show the semivariance of the electrical conductivity, and the last one will show the semivariance of the cross semivariogram. For the graph title, I have indicated that it is the experimental cross semivariogram, and for the subtitle, I have put that the data is transformed with the square root. So now we can run this script. Just like in the previous case, we have the information for each of the semivariograms. We double-click to open it. This is what the new graph looks like. This is the experimental semivariogram for the electrical conductivity. This is the cross semivariogram, and this is the semivariogram for the chloride concentration. I'm not sure if this graph can be helpful in any way, but in the end, it is a graph that offers information in a different way. If the scales or shape of the semivariograms were not clear in the previous graph, this second graph can give us an even clearer idea. The goal of the graph is to have a different point of view on the relations between the different types of experimental semivariograms. For example, this graph is useful to see the range, where we can appreciate that all of them has more or less the same range. And that is an important factor for the execution of Co-kriging. Now, what we are going to do is to adjust the model to the three semivariograms simultaneously. Alright, so to get this task done, we are gonna be using script number 50, which we already covered in the lesson 9 of the third Geostatistics course. To open up the script, just double-click it. First off, we select the target layer, which is the lab samples, followed by the auxiliary layer, field lab samples. Then we pick out the target variable, which is the chloride transformation, and the auxiliary variable, which is the electrical conductivity transformation. We set the cutoff distance to 1,500 meters and the lag distance to 150 meters. For the name of the target and auxiliary variables, we use chlorides and electroconductivity respectively. After that, we input the values obtained from the model we feed it to the chloride semivariogram. I got these values jotted down here for reference. 12.62 for the partial seal, a spherical model, 1,427 meters for the range, and 4.26 for the Niagara effect. Keep in mind that these values are based on the omnidirectional experimental semivariogram of the chlorides, which is our target variable. Once we've got everything set up, we run the script and check out the model results. As you can see in the pop-up windows, we've got the structure data for all the semivariograms, and they all have the same Nagar effect, partial seal, and range values. Now let's take a closer look at what these values represent by checking out the graph. Again, we need to adjust the scale for this script, so let's edit it to set the scale to 20. Save it and run the script again. Double-click to open it up and make the graph bigger. As we can see in this case, we've fitted the model simultaneously to all three experimental semivariograms, but the results aren't great. This means we need to use a different script to provide a better fit to all the semivariograms. We need to understand that when we are using Co-kriging, there is no authorized models like there is with kriging. The authorized models ensures that the structure matrix made up of the partial seal and Nagar effect is positive definite. However, when we create a model for Co-kriging, we have to verify that this matrix is positive definite, since we don't have authorized models to guarantee it like we do with kriging. To ensure that the matrix is positive definite, we have to play around with the adjustment of the Nagar effect and the partial seal simultaneously for all the semivariograms that make up the Co-kriging model. This Co-kriging model needs to meet the premises related to the linear model of correlationalization. Fortunately, we've got an R algorithm that automates this entire process. All we need to do is input the data associated with the target variable structure. Then the algorithm will simultaneously fit the model to the different semivariograms, offering us the Nagar effect and partial seal values that best fit the data and guarantee a positive definite matrix. It is also possible that the fit offered by the algorithm isn't good, in which case we wouldn't be able to apply Co-kriging. At this point, I don't want to go into too much detail about the linear model of correlationalization. That's already covered in the lesson 9 of the third Geostatistics course, as well as the script number 51 that we are going to use next. This script provides a correction for the linear model of correlationalization. If we edit this script, we can change the scale so that we don't get the same error again. The script below allows us to fit the linear model of correlationalization with one parameter that let us select the type of fit we want for the model, and another parameter that lets us achieve a positive definite matrix. So we can change the values of these two parameters to see which ones offers the best fit to the data. In this case, we are going to leave the default values because they provide correct results. If you want more information on this, I recommend checking out the aforementioned video tutorial. So now we are going to save the change and close the windows. Then we'll input the data into the pop-up windows. Lab samples is the target layer, and field lab samples is the auxiliary layer. To account for the target variable, we'll use the square root of chloride concentration, and for the auxiliary variable, we'll use the square root of the electroconductivity. We'll set the cutoff value to 1500 and the lag distance to 150. For the target and auxiliary variables, we'll use the name chlorides and electroconductivity respectively. Then we'll enter the previously calculated spatial structure values for the target variable, which are as follows. The partial seal is 12.62. The model is spherical. The range is 1427 meters and the Nagar effect is 4.26. With this information, we can run the script. When we look at the pop-up windows, we can see that each of the semivariograms has the same range and model. However, they have different partial seal and agar effect values. For the chloride semivariogram, we have 4.30 and 13.24. For the electroconductivity semivariogram, we have 2.57 and 5.50. And for the cross semivariogram, we have 3.29 and 8.45. To apply Co-kriging, it is crucial to ensure that all semivariograms has the same model and range. Nonetheless, it is acceptable if they have varying partial seal and agar effect values. Now, let's open the graph and see how the model fitting was simultaneously performed in all three semivariograms. And as you can see, it is pretty good fit. Now that we have the structure for the Co-kriging model and this structure is valid, let's create the interpolation grid. First, I'll close all these windows. And now I'm going to open the attribute table of the matrix we created earlier for the chlorides. In this matrix, we can see the minimum and maximum distance between the pair of samples. Since the minimum distance is 65, I'm going to create a 60 by 60 meters grid. In this case, I want a pixel dimension value that is close to the minimum distance between two samples. Setting a lower value will generate unnecessary computational cost. Having smaller pixels won't improve the resolution of the raster created by the interpolation. And if we have a larger pixels of 65 by 65, we would lose information in the raster. For example, with a 30 by 30 meters grid, we would have the same information as in a 60 by 60 grid. Then it doesn't worth it to make something smaller. On the other hand, if we have a 100 by 100 meter grid, we would create a raster with fewer pixels, but in this case, we would be losing information since the minimum distance between two samples is 65 meters. First off, we'll select Vector and then Research Tools before clicking on Create Grid. The type of grid we'll create is going to be a rectangle. We want the grid extents to match the perimeter of our research area, with a horizontal and vertical spacing of 60 meters. We'll leave the horizontal and vertical overlay at 0. Make sure the coordinate system is correct, and then I'm going to save the file as a shapefile with the name grid. Now we can run the script. The next step is to cut this grid with the perimeter dimensions. To do this, we'll select Vector again, followed by the geoprocessing tool, Clip, and then select the grid shapefile. We want to overlap the layer with the shapefile named as a perimeter. Once we have saved the new shapefile with the same name to overwrite the old one, we can run this script. However, since we cannot save it with the same name, we'll have to change the file name to grid2. Save it and run it again. After that, we can close the windows and delete the old layer. Moving on, let's edit the new layer. We wanted this layer to be transparent, so we'll select Symbology and choose the option Transparent Fill. The next thing is to adjust the thickness of the line to be thinner. Once we have applied all these changes and select the option OK, what we are going to do next is to create the real grid that we are going to use for the interpolation. Remember, as we did in the previous lesson related with kriging with external drift, this grid that we just created is solely for a visual effects to enhance the pixel display. We are not going to use this layer to do the interpolation. For the interpolation, we are going to create a grid that is based on a point matrix. The algorithm we'll be utilizing is the default one in QGIS, which is the regular points option. To access this algorithm, please double-click on it. In terms of the parameters, the extent will encompass the perimeter, with a point distance of 60 meters. And an additional 30 meters will be appended at the onset to ensure that each point is situated exactly in the center of the cell. Once we have set these specifications, we will save the new layer as a shapefile and name it as point grid. The script can then be executed. Subsequently, we proceed to clip the point grid again using the perimeter shapefile. We will navigate to the vector menu, select Geoprocessing Tools, choose Clip, and designate the input layer as the point grid. We will then select Overlap with the perimeter and allow the script to run. Upon completion, the point grid layer may be removed. As a result, we will have all points from the grid located within the perimeter. In the event that any points are found to be outside the perimeter, they might be removed. However, it is expected that all the points will be contained within the perimeter. Ultimately, it is assumed that all the points are within the perimeter, and thus no verification is necessary. It is presumed that the script will perform accurately. The subsequent step involves the addition of coordinates to each of the grid points. Thereafter, we select the clip layer, which is the shapefile comprising the grid points. We then launch the attribute table, pick up the pencil tool to initiate the layer editing, open the field calculator, and create a new field labeled X, as it pertains to the X coordinates. It is imperative that we stipulate the data type as decimal number, while the length and precision suffice. Subsequently, we navigate to the parameter of the coordinates, wherein we can use the dollar symbol followed by X. Consequently, we need to select this variable. Upon clicking the Help menu, we can observe that this variable avails us of the X coordinate. Double-clicking on the variable, it is necessary to add it to the panel, and then we press OK. We perform the same process for the Y coordinate. The new field shall be known as Y, and it must be designated as a decimal number. We input the dollar symbol followed by the Y, and the Help menu indicates that this variable returns the value of the Y coordinates. Double-clicking to add the variable and pressing OK, it is necessary. Thereafter, we save the change to the layer. And now we have the coordinates at our disposal. Now we can check how many points has this grid. And as you can see, it is 5,447 points. And this is a crucial piece of information that will indicate the number of pixels in the raster image we will have after the interpolation process. Lastly, we close and save the file as a shapefile by right-clicking, selecting Export, choosing Save Feature As, and save it as the grid interpolation in the appropriate folder, ensuring the use of the correct coordinate system. As you can see, when we are trying to save the file, an error was encountered, and this error is related to the layer's geometry. Then what we have to do is change that geometry. In order to address this issue, we will utilize a default script within QGIS known as multipart to single parts. To execute this script, we will first double-click on it, then select the layer that we want to modify, and then we are going to select a folder to save the new shapefile. Prior to doing so, we must remove the previously created layer designated as the interpolation grid, as it lacks pertinent information. Once this layer has been removed, we can refresh the windows and re-add the interpolation grid name. We can then proceed to run the script, effectively resolving the geometry-related error. Let's now ensure that everything looks good with the newly created layer. The coordinates seem to be okay, and here we have all the grid points. Next, we can go ahead and delete the provisional layer. To proceed, we'll save the layer with the grid points as a CSV file. To accomplish this, we'll choose Export and then Save Feature As. We'll select the CSV option in the Format section and save it in the Dataset folder under the name Grid. With the interpolation grid available in the CSV format and the associated data on the spatial structure of the chloride semivariogram, we can proceed to perform the concentration interpolation of the chlorides using the ordinary kriging technique. Next, we'll navigate to the Processing Tools panel, and here we'll open the option for scripts with R. I have provided two examples of scripts, and we'll using the one for ordinary kriging. By right-clicking and selecting Edit Script, we can observe how the script has been organized. It is noteworthy that a similar script was utilized in the first lesson of the 4th Geostatistics course when we was working with the ordinary kriging. However, I made an improvement to this script for this lesson. This new modification enables us to automatically load the CSV file associated with the interpolation grid into the script. Therefore, we no longer need to add the characteristics of the grid, as they are already inherently present in the CSV file. Additionally, the grid characteristics has already been processed in the save file with the QGIS before being exported as CSV file. The significance of this modification is reflected in these few lines and in the line at the top. Nonetheless, the rest of the script is the same as what we saw in the first lesson regarding ordinary kriging. To begin, please double-click to open the script and select the lab samples layer. Next, we are going to select the variable of interest, that is the square root of chloride concentrations. As we have previously justified, our cutoff is set at 1,500 meters, and the lag distance is 150 meters. Moving forward, we'll input the values for the semivariogram structure of the chloride concentration that we have already calculated. For this specific case, we'll be sticking to executing ordinary kriging. The Nagar effect is set at 4.26, and we'll use the spherical model with a range of 1,427 meters. It is important to note that approximately values for the structure will suffice as long as we indicate the same cutoff and nugget. These approximately values has to be added in order the software to initiate the computational process. But in this case, I'm putting the exactly values because I have them, but it is not necessary. Finally, we'll add the partial seal, which has a value of 12.62, and attach the CSV file containing the information associated with the grid. This section is a result of the modifications made to the script. To load the file, we'll open the lesson number 5, then open the dataset and select the CSV grid file. While we do have the option to select the number of neighbors for the interpolation, we'll choose not to impose any limitations on local kriging and we'll use all available samples. For now, we won't save the resulting maps and we'll leave the files as temporary. With all that said, we are now ready to run the script. In the pop-up windows, we can observe the data structure. Additionally, two distinct types of maps are generated. The first is the prediction map for chloride concentration, and the second is the variance map, which is associated with the error of the prediction results. It is crucial to note that with this new modification in the script, we no longer need to concern ourselves with cropping the final raster results, since it is automatically created in the shape that we previously defined while defining the grid. The subsequent step is to reverse the transformation and return the values to their original scales. Therefore, let us establish a new folder called Rasters, and we shall store the maps in this folder. Firstly, we'll save the interpolation map by navigating to Export, Save Feature As, selecting the folder number 5, open the folder Rasters, and saving the file as ordinary kriging. This file contains transformed data. We select Save, ensure that the coordinate system is correct, and then press OK. Next, we can delete the temporary prediction map. Now we shall also save the variance map by going to Export, Save Feature As, providing it with the same name but appending that it is the variance map. Save it and then press OK. We can now erase the temporary file. Now we'll proceed to reverse the transformation and focus solely on the prediction map. To do this, we'll access the raster option and select the raster calculator. In the raster bands panel, we'll carefully choose the map we wish to modify, which in this case is the prediction map with the ordinary kriging transformation. We'll then add it to the raster calculator expression panel by clicking on it. Our next step is to square the selected layer, effectively eliminating the transformation based on the square root. Afterward, we need to carefully select an appropriate folder to save the file. To accomplish this, we'll choose folder number 5, open the raster folder, and save the file under the name ordinary kriging, ensuring that the coordinate system is correct and the format is GeoTIFF. We can now confidently run the script. Now it's time to uncheck the visibility of the sample layers and edit the new raster. We'll right-click and choose Properties, then Symbology, and select Single Band Pseudocolor. Once done, we can add the color ramp of our choice, set the mode to equal intervals and the classes to 10, before finally applying the changes. It is worth noting that we could even invert the color scale, but for the purpose of this tutorial, we'll keep the highest values black. And that, ladies and gentlemen, is the final result for the ordinary kriging. Now let's turn our attention to Co-kriging. First, we'll select the initial script, right-click it, and opt to edit the script. It is worth noting that we can directly incorporate the CSV file with the grid into the script, eliminating the need to concern ourselves with clipping the final raster to the perimeter shape. This script has been designed to automatically provide us with the raster in the precise shape we desire as defined in the grid. Additionally, the following lines demonstrate how to handle the data to ensure the grid functions correctly. These scripts also incorporate the linear model of correctionalization, requiring no modifications. We merely input the variable values, add the CSV file with the grid, and then execute the script to generate the raster. I strongly advise you to meticulously review this script, as it contains a wealth of information and is marginally more complex than the one used for ordinary kriging. This is due to the fact that we are dealing with two variables at once. The target variable, which is the concentration of chlorides, and the auxiliary variable, which is the electroconductivity. It is worth mentioning that overall this script is quite similar to the one we use for ordinary kriging. To begin, double-click to open the script and let's start selecting the parameters. First, we'll choose the target layer, which is the lab samples, followed by the auxiliary layer, which is the field lab samples. The target variable is the square root of the chloride concentrations, and the auxiliary variable is the square root of the electroconductivity. The name of the target variable is chlorides, and the name of the auxiliary variable is electroconductivity. The cutoff is 1,500 meters, and the lag distance is 150 meters. Next, we add the data associated with the semivariogram structure of the square root of the chloride concentrations. Remember, we don't need to make any modification as the script already incorporates the linear model of correctionalization, and it will make all necessary changes automatically. The only requirement is that in this case, the values of the structure must be exactly the ones we calculated, and we cannot introduce approximately values. The Nager effect is 4.26, the model is spherical, the range is 1,427 meters, and the partial seal is 12.62. Then we load the grid. In this case, we'll not be using the local kriging, which will limit the number of neighbors for the interpolation process, as we'll be using all the samples located within the range for the interpolation. Although there is a small error in the script, as we cannot enter the number of neighbors, which was probably removed by mistake. We can add it again. Simple, select edit script and add the necessary command, which can be copied and pasted from the ordinary kriging script. Now we are ready to run the script. Alright, let's close these windows and saving the Co-kriging predictions. To do so, we'll utilize the export and save feature and assign the name ordinary Co-kriging transform and press OK to confirm. The temporary file can then be safely deleted. Next, we'll proceed to revert the transformation by selecting the raster option and navigating to the raster calculator feature. From there, we'll add the Co-kriging file in the raster band panel to the expression panel and square the resulting layer. We'll then choose a folder to save the file and give it the name ordinary Co-kriging, ensuring that the coordinate system is correct before clicking OK. We'll now add a color ramp to the map by selecting single band pseudocolor in symbology menu and assign the same values as ordinary kriging. We'll then select mode, equal intervals, and 10 classes, followed by apply to complete the process. This will allow us to view the Co-kriging map. This is the Co-kriging prediction and this is the kriging prediction. To highlight the interpolation pixel, we can overlap a shapefile onto the grid. If desired, the thickness of the line can be adjusted to 0.05. However, it is important to note that the pixel will still be visible even without this step. The website offers a section where you can download the scripts related to kriging and Co-kriging interpolation, as well as the data information. Additionally, you can download other scripts used during this lesson from the previously indicated lessons. Moving on, our next task is to perform the cross-validation of the two models, the kriging and the Co-kriging. To accomplish this, we'll utilize the leave one out cross-validation technique. First, we'll perform cross-validation for the ordinary kriging using the script number 41, which was created in the 8th lesson of the 3rd Geostatistics course. To get started, we double-click the script to open it and input the relevant data. We'll use the lab samples layer set the dependent parameter to the square root of the chloride concentrations, the cutoff to 1,500 meters, the lag distance to 150 meters. Next, we'll add the values of the structure associated with the semivariogram of the square root of the chloride concentrations. It is important to note that the label here is incorrect and should say partial seal instead of seal, but for now we'll leave it as is. The partial seal is 12.62, the model is spherical, the range is 1,427 meters, and the negative effect is 4.26. The number of beams for the histogram will be 11. And to finish off, we'll title the graph Leave One Out Cross-Validation for Kriging. After inputting all the required information, we can run the script. As you can see, the pop-up windows provide us with the semivariogram structure data and a series of statistical parameters associated with the cross-validation. It also creates an image with 4 graphics that shows the results of the Leave One Out cross-validation. We can maximize the image to get a better view of the different graphics. The first graph is a bubble plot that shows the residual values associated with the cross-validation. Then we have the cuckoo plot to see if the residual values show normality in their distribution. The distribution of the residuals can also be seen in the next graph with the histogram. The last graph is a scatter plot showing the relation between the observed values and the predicted values using the Kriging model. For this last graph, the ideal scenario will be the black line on the top of the red line, since the red line represents the best scenario possible. The farther apart these two lines are, the worse the model is. Ultimately, what we would like to see is that the observed values and the predicted values are the same. If that were the case, all the blue points would be on the red line. If you would like to have a better understanding of the interpretation of all these graphs, I recommend that you watch the lesson number 8 of the third Geostatistics course, where the main topic was the cross-validation. In general, I can tell you that the interpolation with Kriging does not show good results. The residual values are significantly high. However, one positive thing is that the residual values are distributed completely in a random way, indicating that the absence of any trend in the residual values. The histogram presents a normal distribution, but it is somewhat asymmetric due to the high values of the histogram, reaching values close to -10 that are not present on the other side of the histogram. This is also reflected in the bubble map, with the negative very high values and the positive values of the residuals. It is also reflective in the tail of the QQ plot. In conclusion, the results of the prediction of the chloride concentration with the Kriging technique are not really good. In this specific case, if it were not possible to perform interpolation using the Co-kriging technique, another interpolation technique that is not Kriging should be considered because the results with Kriging are not good. Moving on, let's take a look at the root mean square error value for the Kriging model, which stands at 3.138. To be honest, this value doesn't tell us much on its own. However, if we compare it to the value for the Co-kriging model, we can clearly see the difference between the two and evaluate which model offers a smaller error. The next step is to perform the cross-validation for the Co-kriging model. As a heads up, this script is number 53 and was created in the lesson 9 of the third Geostatistics course. To access the script, simply double-click it, and then we can introduce the parameters as we need. First, we'll add the layer with the target variable, which in this case is the lab samples. After that, we'll include the layer with the auxiliary variable, which is the field lab samples. Next up, we'll input the target variable, which is the transform of the chloride concentration, along with the auxiliary variable, which is the transform of the electroconductivity. Following that, we'll set the cutoff to 1,500 meters and the lag distance to 150 meters. Then we'll input the semivariogram structure for the square root of the chloride concentrations, with the partial seal at 12.26, spherical model, a range of 1,427 meters, and an agar effect of 4.26, and the number of beams will be 11. Lastly, we'll give the graph a title of Leave One Out, Cross-Validation for Co-kriging. It is important to note that for this script, the parameter values for the structure must be exact. With all that in mind, we are now ready to run the script. In the pop-up windows, we have again the values for the structure. In this case, we have the structure for the two direct semivariograms and for the cross one, and also we have a series of statistical parameters. Furthermore, when we compare the root mean square error of the two models, it becomes evident that the Co-kriging model has much smaller error rate, with a value of 0.999 in comparison to the Kriging model's value of 3.198. This difference is significant, with the Co-kriging model being 3 times more accurate. Next, we can open the graph created for the Co-kriging model. As you can see, the bubble map displays much smaller residual values, ranging from 2.5 to minus 2.8, as opposite to the Kriging model's residual values, which range from 6.7 to minus 9.7. These observations further highlights the superiority of the Co-kriging model. The scatter plot, which compares the observed and predicted values, illustrates a strong correlation between the two sets of data. This is demonstrated by the majority of the blue points falling near the red line, which indicates a very good model fit. The similarity between the black and red lines also reinforce this observation. Additionally, the histogram shows a normal distribution with a symmetrical shape, further confirming the accuracy of the Co-kriging model. Although the QQ plot has long tails, this is a common phenomenon and doesn't necessarily indicate a lack of the normality in the data. It is important to note that the normality of the data can be clearly seen in the histogram. One thing that really catches my attention is the predicted values with the Kriging, where the range in the raster goes from 39 to 328, while if we look at the original values in the lab sample shapefile, we see that the chloride concentrations goes from 14 to 387, and here it goes from 39 to 328. We already know that Kriging is not an exact interpolator when there is Nagar effect, but in this case the interval we are getting with the predictions through Kriging is really far away from the actual values. When we compare the real values with the values obtained in the raster formed by the Co-kriging model, we see a substantial improvement, with a minimum value of 17.37, while here the minimum value is 14, and a maximum value of 381, while here it is 387. In the end, the values obtained with the Co-kriging model fit much more closely to the reality. As mentioned before, the predictions with ordinary Kriging in this case are not really very good. However, the predictions obtained with the Co-kriging are significantly good, indicating that the Co-kriging model is objectively quite good, as the data shows. This is the end of this lesson and also the end of this 4 Geostatistics course. I hope you enjoy with this course and see you on the next one. Thank you very much for watching this tutorial and see you soon.